Our next topic is circular current loop as magnetic dipole. So we have already seen this circular current loop, but now we are going to see it as a magnetic dipole. So there is a correlation between magnetic dipole and this circular current loop that we are going to see. We shall show that the magnetic field at large distances due to a circular current loop is very similar in behavior to the electric field of an electric dipole. So previously we have seen what is the electric field at very large distances. So this is our circular loop and current is flowing in this loop. So if we take very large distances, suppose this is the x distance and now this x is very large. So this is the radius of this loop and this distance x is very large. Then we have to show what is the magnetic field due to this circular loop, and we will find that it is very similar to in behavior to an electric dipole. Now previously we have seen the magnitude of this field is B is equal to mu naught I r square upon 2 x square plus r square to power 3 by 2, that we have already solved previously in this chapter, that for a single current loop the magnetic field on any point on its axis. So this was the formula that we have got. Remember, this we have solved, where this was small r, this was capital R and this was x. But now we are taking, previously we simplified this formula when we were taking the field at the center. At center x is equal to 0. So let us put x is equal to 0. So this is gone. R square will become r cube, because of this 2 and 2 cancels out, and r square also cancels out, only single power of r is remaining. So what is formula? Formula is mu naught I upon 2r. That formula we are using for a very long time, mu naught I upon 2r. But this time we are going to see when x is large, not x is 0. So this time x cannot be ignored. So we take x very large. Since x is large, this time we are not going to put x is equal to 0, we are going to put this r equal to 0. Then what will happen in this case? Since x is large and this r is small, so let us see one case. So this r is small, x is very large. So if in this case we see this, so we can ignore r in comparison to x. So that is the case we are solving. So let us remove this. So what we have? So we have this formula mu naught I r square upon 2, this is gone, x cube. So this is the formula we have now when we remove this r. Remove, or we can say neglect this r. Now let us go further. Now we know one quantity, that area of the loop is pi r square, that is clear to you. So this area is pi r square because it is a circular loop. So let us put this mu naught I, r square was already there, we multiplied it with pi and divided it with pi. This pi r square will become a, and in the denominator we have another pi. So mu naught Ia upon 2 pi x cube. As earlier defined, we define the magnetic moment. So we know what is the magnetic moment. Magnetic moment is simply Ia. So this was in magnitude, and now this is a vector form. M is equal to Ia. So B will become mu naught, this will become M, and this is 2 pi x cube. and you can see that we have changed this sign to nearly equal to. Nearly equal to because we have considered that this r is very less and this x is very large. So that's why we have changed it to nearly equal, because we consider this r to be 0 but r cannot be 0. So this will become mu naught upon 4 pi. We again multiplied by 2 and divided by 2. So this mu naught, this 2m is here and this 2 pi becomes 4 pi x cube. So this is the new formula. Why we have put a nearly equal sign? Because we have considered r is equal to 0 but r is not equal to 0. Let us see this expression. The expression of 4.31a, this one, is very similar to an expression obtained earlier for the electric field of a dipole. If you remember, we have solved the electric field for a dipole and we solved for two cases. One case when point is in the axis, point is somewhere on the axis connecting this dipole, and another case was that when the point is somewhere on the in the plane bisecting this line of the dipole. So there were two cases. First, when this point was on the line, and another case when the point is on this perpendicular bisector plane. These were the two cases that we solved. Comparing it with that case, if we change this mu naught, so you know mu naught is a constant. Let us change this mu naught with another constant 1 by epsilon naught, and this magnetic moment with the dipole moment, and this magnetic field with electric field. So what we get? We get this is changed with E, and this 2 is already there. This m will become Pe and this mu naught become epsilon naught. So this is 2 Pe upon 4 pi epsilon naught x cube. So this is the same expression that we have got for the case of electric dipole when the point was on its axis. So here we can see that both the expression this and this are very similar in nature. Only we have changed few quantities with their alternative quantities in electric field, which is precisely the field for an electric dipole at a point on its axis. So we have solved these two cases. So first was that, so this is the axis of the dipole and we have solved, let us say this point was there or somewhere here. So this was the case when we solved electric field on the axis of this dipole. Another case was when point was on this plane, equatorial plane. So there was a plane which is called equatorial plane. So this was the another case. So that were the two cases when we solved, and we saw that the electric field on equatorial plane was half of this on the axis. Now the electric field on the perpendicular bisector of the dipole, we can say that perpendicular bisector, or we can also say equatorial plane. So that was half of this, just half this. So this will become 2 Pe divided by 2, that means Pe upon 4 pi epsilon naught x cube. So that can also be checked. So that for electric dipole we have already done that. We have already got this equation for electric dipole. Now here x is the distance of the dipole, the distance from the dipole. Again let us substitute this P, change P by m, mu naught change by 1 by epsilon naught, and B will become E. So let us put these changes. So what we get, E is changed by B, this 1 by epsilon naught is changed by mu naught, this P is changed by M. So what we get, mu naught M upon 4 pi x cube. This is the expression for the current loop at large distances. This is only valid when x is much larger than r. The result given by the equations, so we have got previous equation where we had 2m and this equation where there is only m. So these two equations become exact for the point magnetic dipole. So that means if this loop becomes small and small and small and it becomes a point, these results will become exact, because in that case r will be 0.